right? Industrial rollback. So today we are going to move on to the next data structure, which allow you to increase that performance by a big deal. I mean, you can obtain the performance of big O log to n, which very good for our course. So it's about tree data structure, and from now on you will see it a lot. So let's go on. We have something to talk about today. We are going to discuss some basic concepts first, and we discuss about the binary tree as well as a particular application of that one, expression tree, and finally we are going to talk about binary structure, which is the simple one. All right. So first, let's talk about some basic concepts. So we have something like this one. A tree is nothing but a special case of a graph. We are going to talk about the graph at the end of the course, but right now, the tree can be considered to be a special case of the graph where you have no cycle in the graph, okay, and there's no, there are some other properties you may have. But anyway, a tree is a finite set of elements, right? We call that node, and a finite set of branch, they call it branch, right? Directed line coming from one node to the other. And so one node may have either no incoming branch or at most one incoming branch. Because if one node has two incoming branch, that's no longer a tree but a graph. Okay? General. And a node may have multiple outcoming branch or either no outcoming branch. That's our decisions to make. Now, for the tree, what you see here is that we have some sort of relationship in the tree. The node B and D over there are some nodes staying in the middle of the tree. We call them intermediate node. While A is a special node because it stays on the top of the tree. It has no parents. And so that one we call root. Just like the image of the tree you see out there, there's root, right? Then that node, the top one, is called root. And some node that has no children, like E, F, C, G, H, I, all of them are called leaf because they have no children. They're supposed to be the end point. Okay? So that's the relationship. And in the tree, we have some other relationship like A is the parent of B, and B is the child of A. Likewise, we have EF, a child of B, but B is the parent of E. Okay? There is no such concept called grandparents or grandchildren. It's unlikely that you see EF as the grandchildren of A. No, we don't have that concept. We only care about the direct child and direct parents. Okay, so keep that in mind. So also in the tree, we have some concept called sibling. So B, C, D are siblings because they belong to the same parents. Okay, E, F also sibling. G, H, I are siblings, but F and G are not because they belong to different parents. Okay, even though they stay in the same level. And there are some other concepts called level. Well, the level of the root A is always 0. That's the beginning. And so the level of B, C, D would be 1. The level of E, F, G, H, I would be 2. All right? And there are some other idea about the path. Well, the path from A to G will be a segment of node that you have to travel along the way in order to reach G. So the path to G will be ABG. Okay? The height of the tree is going to be the maximum level of the node plus 1. So the maximum level in this case is 2. So the height of the tree will be 3. Okay? Easy? So that's some basic concept we need to discuss. And one more thing. We have so far everything we need for the tree, but there are some limitations we need to set up for the tree also. And those limitations are the relationship between the height of the tree and the number of nodes. So given n node in the tree, then what you're interested in is what is the maximum height of the tree as well as the minimum height of the tree. So if you have n node and the tree obtains the maximum height, then it means the tree looks something like this one. I don't know, but every level only have one node. Okay? And if that is the case, then the maximum height is going to be exactly n node, right? When the height of the tree is minimum, then it means at every level, every position will be occupied. Okay? So we are going to talk about it in the other topics, because right now we are just talking about some basic concept of the tree. So if you don't know how many child you can have, then you cannot set up this number. Okay? So let's wait a little bit longer. Here are some things that you need to remember about the in degree as well as the out degree. The in degree of the node is the total number of the branch, the incoming branch to that node. And the out degree is the total number of outcoming branch from that node. So for example, D has in degree 1 and out degree is 3, just like you see in the picture. And A has in degree 0. A obviously the root. So the root has in degree 0. Okay? And our degree of some node can be either 0 or larger than 0. So if our degree of a node is 0, like C, E, F, G, H, I, then it means they are leaf of the tree. Okay? And if they are larger than 0, then those nodes will be the intermediate node of the tree. And there are some more concepts that we just discussed earlier, and you can check out later. Again, those are some terminology that we have for the tree in general. We are talking about the tree in general, right? And again, these are something very basic, so I don't need to repeat it, right? There are some examples that you may want to check out at home later. These are subtree, very easy, right? Now, when it comes to representing the tree, what we care about is how do we represent that tree in a way that people or humans can understand. So the simplest way for us to do is drawing the tree like an organization chart. This is very familiar with all of us, like your family tree can be drawn this way, or your companies may have the organization structure, something like this. Okay, from CEO to CTO and some other people below, like project manager and team leader and so on and so forth. So it goes in this hierarchical order. So this one is the representation that we use a lot from now on to the end of the course, because it's very easy for us to imagine how this tree is organized. However, there are some other ways to representing the tree using the parenthetical listing. This goes like the node and open bracket and child. So it's like a list of child inside the bracket. And if you look at this tree, what I can do when I write this is going to be A is the node, and then open bracket, I should have some child. The first child is going to the tree B. So B is the node, and B should have some child. So it's going to be E and F. And then I see another child C. And then I see another child D with child G, H, and I. Okay, so this is the first subtree, second subtree, the third subtree. In B, we have E is the subtree, F is the subtree. For D, G is the subtree, and H is subtree, and I is subtree. Okay? So the problem with this one is, can you tell? What is the problem of this representations compared to the organization chart? Sorry?
Too many brackets.
No. The number of brackets is it's not a problem. What's the real problem? Too hard to visualize. We care about the structure of the tree, not visualizing things. What happens? Can you tell? It's not so obvious, right? Why this one is not working? Tell me.
Not enough. Not enough character.
It's not about the characters. It's just anyone. Okay. Let's say I don't have C. Then what it means? If I don't have C, what it means? Like for this tree, I have A with three subtree. One is the leftmost, one is the rightmost, and one in the middle. So if I don't have C, look at the organization chart, I still know that B is the leftmost tree, D is the rightmost tree. Right? So that organization chart gives you some information about the positions of the subtree in terms of visualization as well as representing that position. But if you look at this one, if you don't have C, then there's no way you can tell if B is the leftmost or the center. Likewise, D, you don't know if it's the rightmost or the center. And that's bad, because all you have is a list of subtree, but you don't know their positions.
Why don't they have this last one?
Oh, yeah, good idea. Like some sort of blank space here, right? That's okay. You can have that definitions. But again, even if you have this kind of definition, maybe the way we read that list is harder than the way we visualize the data. Okay? So good idea. If I don't have some node in the middle, then I should get this one. But again, if you have many subtrees, then the tracking of position is very hard. In fact, so be careful with that. And this is why we don't use this one very often. Sometimes we use it, but not so often. And the indented plus over there on the right side is also popular. You see that when you work with the directory structure, right? you use computer a lot, when you open the Explorer, you will always see the directory tree. And the leaf in that one is always the 5. And the intermediate node will be the folder, right? And you will always have a root folder somewhere, okay? Especially important in Linux. You see that in Linux, everything starts with the root, right? So again, the application of tree is very important. It can be applied in a lot of applications like the database. How do we store the data in order? How do we organize the directory structure? How do we manage some searching organs just by using the tree? And that is why we are discussing about the tree in this session. And there are some applications here. I guess you may want to check out it at home. Now let's talk about binary tree. Well, the binary tree is a special tree where the join of each node is at most 2. Well, you cannot have more than 2 join for the node. So that's why we have the word binary. Binary is 2. Okay, and the binary tree is actually an extension from the link list. So previously, what you see in the link list is the link to the next element. Like this one. Now for the tree, we extend that concept by adding one more link. Okay, and this goes like this. But drawing the tree like this is kind of hard to follow. I mean, it's very annoying and it's not natural to us. Most of people prefer drawing the tree just like organization chart. Okay? And so when it comes to binary tree, we have to define some operation on the binary tree, right? So what operation do you think we can do with the binary tree? What kind of operations? Insert. On. And what? What else? Move. What else? What else? Bring down. Okay, that's traversal. Just like this. In a list we have traversal, so in the tree we should have traverse. What else? Find the height of a tree. Oh, okay, interesting. What else? Sorry? That traverse. What else? What else? Come on, that's your homework. Okay, so let's go like this. As we are talking about binary tree, we set up no order in the tree, right? And because you set up no order in the tree, it's hard for you to decide whether you want to insert a node to the left side or to the right side. See? When you have no order, then it's not possible to decide whether to check to the left or to the right. So, right now, at the moment we are standing here, talking about binary tree, we're not caring about insert or remove. Not even fine, because if you set up no order in the tree, there's no way for you to find something in the tree. If you want to find something in the tree, you have to find on the left and find on the right also. It's like the brute force. Always look for everything. And the performance just as poor as this. So why do we do that, right? So we are going to not discuss about that one, but maybe traverse and get paid is possible. Now for traverse, so we have two ways to traverse on the tree. We can traverse on the fashion of lead first or in the breakfast. To make it have a tree something like this, A, B, C, D, E, F, G, H, I, J, K, L, M. Okay, suppose that I have a tree like that one. Then you can decide to traverse on the direction like this one, from left to right, from top to bottom. And if you do so, we call that traverse, because we go in this order. Okay, we go wide instead of go deep. And if you go deep, you will go in this direction. So you prioritize the node below it until you reach the leaf. For example, I may go from A and then I see, oh, I have to try B and D. So instead of browsing B and D at the same time, I will go for B first. And then for B, I see E and C, F and C, so I will go for F first. So I go in this direction, go deeper and deeper until I reach the end point. And then I backtrack and I go for another level. So that's how we do it first. We go deep. And the principle of the lead first is going to follow the recursion algorithms. Alright? So for that first, we have three orders. We have that first as well as breakfast. But breakfast is simple because for breakfast you traverse on the node and then you see some child of that node, but you don't decide to traverse on that node right now. You have to make them wait. Then the idea is simple. We are going to put them into a queue. So the traversal order of breakfast will be something like this. Okay, but for that first, it's a little bit different. We may be interested in browsing the node first, and then the left tree, and then the right tree. You may also be interested in browsing the left tree first, and then the node, and then the right tree. So depending on that order, you may have different kind of that first. Either node, left, right. This one we call pre-order. But for this pre-order, we have several variations. This one is one of them. The second one is node, right, and left. This is pre-order. Okay? You may have another variant called in-order. In-order means you browsing on the left tree first, and then you work on the node, and then you work on the right tree. And this one is the most popular in-order we are using. Then you have browsing on the right tree first, browsing on the node, and the left layer. This one is also in order, but in the reverse direction. And then you have the post order. You browsing on the left tree first, the right tree, and then the node. You may have another variant, right first, left, and then node. Okay. So regarding this, we can easily write the order here. Let's say I go for the nodes first from the root, and we have A. And then for the left tree, I will have B is the first node, and then I will keep going for that direction. So the left of the B will be F. F has no left, so I will let it blank. F has no right, so I let it blank. Then this C, and then C has one left, so I go there. H. And then as we have no right for C, we come back here. So the order you observe is from this direction. Looks like you are going along the border, and then D, E, I in the process. This is where we go. So we will have C, H, and D, E, I, J, K, M, G, L. It's super easy, right? It's super easy. This is how we do the, oh, sorry. This is super easy, not left, right. And what about not right, left? For not right, left, we go in the similar order, but in a reverse direction. So I'm going to have A, D, G, L, E, J, K, M, I, N, B, C, H, and F. Easy, right? All you have to follow is follow the border of the tree, either from left to right, counterclockwise, or from right to left, clockwise direction. What about in order? Well, in order, like you have, let me split this one. Or in order, then we have the node in the middle, so the node is A. Then you have the left tree. The left tree has the node is B, so B stay in the middle. B has the left tree F, so F stay here. Right tree of B is C, C stay here in the middle. And C has the left, that's H, so H stay here. C has no right, so that's fine. For the right side, we have D. For the left of D, we have E. For the left of E, we have I. For the right of E, we have J. For the left of J, we have K. For the right of K, we have M. Okay? And for the right of D, we have G. And for the right of G, we have L. This is in order. And the easiest way for you to traverse in order is you shift the tree up. So if you shift the tree up, what you have is going to be K, M. This one gives you K, M, J. This one gives you, if you shift them up, will be I, E, K, M, J. If you keep the shift them up, this is L. Shift them up, D in the middle, right? So we have I, E, K, M, J, and G, and L. Right? And this one gives you S, C, this one gives you F, B, S, C, and then you push them up, A stay in the middle. Just exactly what you see here. F, B, S, C, A, I, E, K, M, J, E. That's it. That's in order. Okay? Easy? That's it. What about another in order? Well, reverse that. So you have L, G, D, J, M, K, E, I, A, C, H, E, F. That's easy too, right? So they are dual form. If this one you have, then you have this one directly from this one. Yeah, dual. Okay? What about this one? Of course, if you do this one, you will see that it's very annoying because you have to travel the note lastly. So you put A here, and then you traverse the left tree, which is B, and then you will traverse on the right tree, which is D, right? But do I have to follow that process? No. What actually happens here is this order is going to be, let me read, F, S, C, D, I, M, K, G, D, L, G, D, A. Because this one is actually the reverse order of this one. They are dual. Right? Note, right, left, left, right, note. It's just the reverse. So why do I have to worry? If I can write the pre-order that easy, then the post-order is so that easy. And so this one is also another reverse order of the first one. Simple, right? Right. So in the end, writing the order of the note is not hard. All you have to remember is how to work on them. Right? So for the pre-order, you follow the border of the tree. For in-order, you can shift every note up, in the bottom up directions. That's easy. Okay, that's for traversal. For breakfast, we will use the queue to apply that method. When you see some subtree, you put them into the queue. And we keep repeating browsing the queue until the queue is empty. That's the idea. How about looking for the height of the tree? Well, you look for the height on the left side, and you look for the height on the right side. Which one is larger? You take the maximum. But it's like the brute force algorithms again. There's no smart setting here. You have to look for every, or in the end, you have to traverse all the elements of the tree. And that's the problems. It is so annoying. But that's fine. Okay, so we have every basis order for the tree. But again, we are not going to implement this binary tree right now because it's no use. If you want to build a tree, you have to build from bottom up. It means you should have the subtree on the left, you should have the subtree on the right, and then you make a new tree from that. And you keep bottom up because we set up no order. Therefore, when you insert something into the tree, you don't know what to insert. Right? So it makes no sense for me to implement the tree right now at the current state. That's some basic concept about traversal and finding the height. That's fine, but we don't do it right now. We care about the content later. Okay? So if you take a look at the material, you will see some information like how do we define the subtree and the right tree as well as something. But yeah, for the binary tree, there are something about the maximum height and minimum height. This has something to do with the log 2, right? Because the binary tree is the tree with at most 2 subtree on every node. Therefore, it's easy for us to derive this the minimum height. The tree has the minimum height when every level is occupied. Right? Like this one. If you have the tree like this, then it means every level is full and you have no way to insert some node into the tree, right? And if this is the binary tree you have at the maximum number of nodes, then the height is the minimum, right? Even n node, and this is gonna be the structure of the tree when the height is minimum. So the minimum height would be, well, let's calculate the relationship here. This is 2 power O, this is 2 power 1, this is 2 power 2, this is 2 power h minus 1, right? So the sum over them will be 2h minus 1, right? And this gives you number of node maximum given the height, right? Given the height h, this is the maximum number of nodes. Therefore, the dual form of it gives you the minimum number of height will be log 2 of n. But let me take the lower bound, the floor plus 4. You can verify this one, alright? That's not so hard. So this one is a dual form of this one. Likewise, you have the h max, therefore you have n min. N min equal to h. This is dual, right? Is it? So that's for binary tree. Now, the thing you are seeing over there is like a spoiler about the balance. Because when it comes to a binary tree, there's no way for you to control the shape of the tree. Right? Without any setting, right now the tree has random order. It depends a lot on how you insert the data into the tree, but you cannot control it. And for that reason, the tree is unbalanced. So when I say the tree is unbalanced, I mean we have some way to measure the balance of the tree. The balance now based on the height of the tree. So if the left tree and the right tree has similar height, then they are balanced. Similar means they differ no more than 1. So for measuring that, they take the height of the left, subtract by the height of the right, and we call that the balance factor. So if they are equal, then the balance factor is 0. If the left is higher, it will be 1. If the left is shorter, it will be minus 1. But the tree will get unbalanced when that factor turns out to be 2 or minus 2 or even out of that range. Okay? So that's some sort of spoiler because we are going to talk about it later in ABL. Not today, but yeah, we are going to talk about it in ABL. Not now. So don't worry. It's just some concept. Well, there are some other concepts that you may want to remember. This is about the complete tree or nearly complete tree. So a complete tree is the tree satisfies this condition. The number of nodes is equal to exactly that number, 2 power h minus 1. If you have a tree, the binary tree, with the number of nodes equal to 2 power h minus 1, where h is the height, then this one is called the complete tree, complete binary tree. There is another tree called nearly complete tree. The nearly complete tree means a tree with the number of nodes and is somewhere below 2 power h minus 1 but greater than 2 power h minus 1 minus 1. This is the condition, necessary condition, but not yet. This condition says the number of nodes must satisfy this condition, but another condition is at every level except the last level, every level except the last will be full, which means from here to here, the number of nodes is full, but the last level may lack some nodes. But all the nodes on the last level must stay on the left, which means if you have a tree like this one, it's not a nearly complete tree. It's not. And this is very strict condition. Everything in the last level must stay on the left side. Must not should. Okay? This is nearly complete. And this is important. You have to remember that one. All the nodes here must be occupied, but on the last side, the last level, the left side is occupied, not anything in the middle on the right side. Easy? So far so good. Now why do we need the concept of complete tree and nearly complete tree? Because if you encounter some tree which is nearly complete tree or complete tree, then you don't need the link structure. In other words, you can use an array to represent the tree. Because the array in that setting give you a way to address the relationship between one node with their child and with their parents. We only need the index to do so. But right now, I don't bring that concept up because we are going to discuss in some other data structure later. Not yet, not now. Just to make sure that we can have another representation using array to represent the complete tree or the complete tree. Okay, keep that in mind. Any questions? Okay, so let's move on. You can follow the material to see some other definition as well as an example. It will be easy. Right now, for this one, we have the pseudocode for define the basic of the tree, the binary tree. Now, one thing I want to remind you is that for the data, your data may consist a lot of information, but there is something you have to remember is the key. How do we compare elements is important, right? So to compare two elements, we base on the key. That key conceptually can be some numbers, but it can also be some function to measure the difference. Okay, you may want to measure the difference between two students by the GPA or by the birthday or something else. Who knows? Okay, it's just a way to compare the data. So the key here, just like a concept to tell you that we need something to compare between the data. Okay. And for the node, now we expand that pointer, the next pointer, to make it left and right pointer. And for the tree, all you have is the root. And this is what I mentioned earlier. All we need to do for the complete tree or nearly complete tree is using that array. And we can use array very efficiently in this setting. For the traversal, I have just talked earlier. So this one is just like a note for you guys to read at home. I will skip this one if you don't know. Okay, let's talk about a particular application of the tree, which is called expression tree. I don't think this is the most important application, but it's give you some insight about the application of the tree in a general setting. Well, expression means you can represent some sort of calculations using the tree, right? You know that in math we have some unary operator as well as the two binary operator. What should I call that? Plus, minus, or multiply or divide. These two operand operator, right? Yeah. 2.2. Anyway, so the way we bring up the expression tree is because if you represent some sort of expression, we can use the binary tree. Okay? So for the binary tree, the important thing in the setting is that Now a node can be an operator for a value. We don't know. So if you want to construct this kind of expression tree, you have to be very carefully design your data structure. By saying that, I mean you have to understand and utilize the concept of abstract data type I mentioned earlier. So when you define a node, that node should have some sort of method for evaluating the value of that node. And it should have some pointer onto the real data. So that real data can be a function to calculate something, or it can be a pointer onto some data. For example, here you see an expression A multiplied with C plus B and all of them plus with D. Then B plus C can be two nodes. B is the one node, and that node has the pointer to there. Okay? C is another node that has the pointer to the there. So when you evaluate the value of that node, you will return the value of that pointer. Okay? But the plus node here, that node is a node with a function pointer onto a function. And when you evaluate the result of that node, you have to evaluate the result of the left tree and the right tree, and then plus them together by that function, and then return the value in the end. Okay, that is why you have to design some sort of abstract data type here. Okay, but I guess because you have some trouble at first if you want to make the expression tree. So what I'm showing you here and what I'm discussing here is to give you the insight on how to make it. Well, a tree is not necessary to contain the same data on every node. It can contain anything you want. The important thing is you have to define your node as something very abstract so that it can be, well, changing very complex depending on the situations. So in this case, we have the expression tree. Now why this is better? Because later, when you learn about some programming language and you learn about how to construct a programming language, you need to know how to construct this kind of computation graph. Because A, B, C, and D can be a placeholder. When you define some sort of expression, A, B, C, D now can be some sort of memory, which may not have some value at the beginning. But during the runtime, you may feel the value for those memory. Okay? And the expression, when you evaluate, it will try to query the value of those placeholder to calculate. Think about it. You want to calculate this expression A, B, C, D, and I only initialize B and C, but A and D are empty at the beginning. Then, during the process of evaluating, when I try to evaluate the value of A, I see this is empty, so I will ask the user to input that one for me. Or may I read that in some file? Okay? So defining the data structure this way has a lot of advantage, and it gives you some sort of flexibility during the operation of your program. But again, it's very complex if you want to construct such kind of programs. But you have to. Next year when you learn about the EPL, you will know how to construct this one. It's important. Right now, as we are learning about DSA, you can already construct this tree. But the application of it is not so clear until you learn about how to construct a programming language. Okay? So let's wait until that moment. But that's fine, right? When you have the expression tree, you can traverse on the tree to get that kind of readable expression. for the tree, you cannot grid, right? But you can traverse on the tree to construct some kind of expression like this, and we human can do this one easily. How to do that? We apply in-order traversing, right? You can apply in-order traversing to do so. And in order to evaluate the expression from the tree, what do we do? Post-order traversing. You evaluate the value on the left, you evaluate the value on the right, and you calculate the value from this node operator. That's the idea. Okay. So here are some pseudocode for making the tree, but I guess this is so simple, right? So you don't need to worry. I just put there for the reference purpose. Now, the main part of today's talk is about binary search tree. And read carefully. This is the search tree, which means the tree is constructed for the purpose of searching. And the implementation of that is binary tree. Be careful. This is not a binary tree from the beginning. This is a search tree, a tree made for searching. But the implementation of that one is binary structure. Okay? And given that, what you see is that we are going to set up some sort of order on the tree. Because if you want to look for some data, you must define how do you compare elements, otherwise you cannot search efficiently. It's just like brute force, like I mentioned earlier. So here, for the BSD, we have the left tree. All the elements on the left tree is smaller than the node. And the right tree, all the elements will greater or equal than the node. Let's just agree that this is the order we want. Some of you may want to say, okay, the left is smaller or equal than k, and the right is greater than k. That's fine. But to make sure everyone on the same ground, I will follow this kind of saying. Okay? Yes. As to set up the order, you can now implement every order we have for the binary search. Then, just like we mentioned earlier, there are three basic methods over there, and we will implement that one. So first, let's make a tree. It's like watching Indian movie. Okay. Okay, give me a sequence of numbers, please. Random. No. Just random, please. 1 person only. 18. And 9. 4. 36. 36. 69.
2018.
You love this number, right? Okay, everyone loves it. What else? 3. What else? Minus 4 and 54 and 0. 14. Lucky number. What else? What else?
Minus 17.
Minus 7. What else?
Can we just float?
So,
Can we float?
just for demonstrating, don't make float number. Just
11.
14 or 14. Okay, I think that's enough. So let's make the tree. At first, you have the empty tree, right? Then you insert the number 18. So as the empty tree is there, what we do is making a new node, and then you have 18 over there. Then you have 9 insert to the tree. So this tree is not empty, but 9 is smaller than 18. So we insert that one. Remember, we insert that one to the left. But the left is empty now, so we make a new node. Okay. 16. 16 is greater than 18. It's empty. So we make a new node here. And from now on, I will make it quick. Okay. So we have 69. We have 3. We have minus 4. We have 54. Oh, okay. 54. 0. No. It's here. Right? The way we go down is here. 13. 13 gives you here. Minus 7. Minus 7. 40. 40 gives you this one. So this is the binary tree construct from this sequence of number. The problem we have is that you cannot control the shape of the tree, because even though we set up the order, the way you insert the data affect a lot in the shape of the tree, right? And for that reason, no one will use the BST. Why? Because if you cannot control the shape of the tree, you cannot guarantee the performance. The performance for the tree in this case, in the worst scenario, is OM. But in the best scenario is O of log to M. But the best scenario is hard to appear because there's no way you can guarantee. Okay? That is why we are going to learn about the balanced tree later. But right now, as we have the binary tree. Then let's finish our insert order, right? Extremely easy. Let's do find. If you want to find something, all you have to worry is about the key. So if the key is equal, you found it. If it's smaller, you go left. If it is greater, you go right. That's all. So I think this one is easy too. Let's conclude that one. Last is remove. Which one do you want to remove?
9.
Which one?
9.
9. Okay. If you are about to remove 9, then you have to put your hand here and you see that something is missing in the middle. So if you completely remove this node, that means the structure of the whole tree now needs to be modified. And that is bad. So in order to remove something out of the tree, we have to roll some cases first to see which case is easy and which one is not easy. So this goes like this. The first case, you have a node, and if the node is deleted, okay, that's easy. All you have to do is delete that one and make the root 2 be null. Right? That's the first case. How about the second case? For the second case, you have the left is not empty, but the right is empty. If this is the case, then you have to hold this one and update the root to this one and remove this one. This one is easy too. No, sorry. Sorry. This one will hold the left, right? Because the left is not empty. the third case, similar. You have a node, the left is empty, but the right is not empty. So you call it, then you modify the node here, the root, and this one should be deleted, right? So this case, and this case, all of them are easy. Now, the troublesome case is here. You have the root, you have the left, you have the right. And as I mentioned, this one is troublesome because you don't want to remove this node, but instead you want to change this situation into either this situation, or this situation. You push that process into the left so that we can solve it easily, right? And in order to do so, we are going to pick up the maximum on the left. We clone to this one, and then we remove this one. Or we pick the minimum on the right, and we clone to this one, and we remove this one. So, time for voting. I hate it when I ask, what do you eat today? You say whatever. That is the bad answer ever, especially for girls. So, have to be very clear here. If you want to keep that relationship stable, you must be clear about what you want to eat. Clear. Either left or right. Left. Who say left? Raise your hand.
Gì ta cha?
You failed the course. Whatever. Left. The major argument. Who picked the right? That's one. 2, 3. Yeah.
Con gái như tay phải.
Okay. Listen. The reason why I asked this because this would matter. There's one right and one wrong. Let's see. Suppose that I have a situation like this. I don't care about this one. Whatever. Let's say I try to remove 5. Then, as suggested over there, I will try to pick the maximum on the left. So maximum on the left is this one. I put 3 over here. But remember, what you are doing is you are comparing the key, not the data. So even though the key is equal, the data are not equal. They are different. So I pick the maximum on the left, which is 3. I clone here, so you get 3 over here. Then you try to remove 3 out of the left, but 3 is here. So what you are about to remove is you put 2 in the place, and then you remove 2. So in the end, what happens? Something is not supposed to be removed, now being removed. Something is not supposed to be there, now is duplicated. This is because you set up the order like this one, smaller and greater or equal. If you set up the order this way, then you will encounter these situations. So, don't pick up the maximum on the left. This one is wrong. Then you have to pick up the minimum on the right. But again, it depends on your setting. If your setting is the left is smaller or equal, the right is greater, then if this one is the case, maybe you have a different situation. Okay? But again, we start from the beginning that you stick with this one, so don't pick up the maximum on the left because it gives you these situations. Okay? So that's it. We are going to pick the minimum on the right for a reason. Okay? So that's it for BST. Now it's time to play with the code a little bit. And it's very easy, so let's start. Slow motion. This is where we are. What do we have? We have this. We have stack. Then let's go. Let's do the tree. Let's view a forest. Okay. Let me make first, let's define the interface for your class first. But I guess I don't need to. Just say I have a class of binary search tree. Okay? Then you need to define the data structure for the node. And I don't want user to see it, so I make it protected. Let me define the struct of the node. Okay, for the node you need the data T. And you need some sort of pointer to the left and the right. So you need node. Sorry, my bad. So you have the pointer to the left tree and the pointer to the right tree. Okay, so that's it. We should provide some constructor. Therefore, I would provide the first constructor, which receive value, right? So value, and what else? It should initiate the left and the right tree also. So we should have the node P left, and we should have the node P right. Okay. So by default, the node on the left should be node, of course. By default, the node on the right should be the okay. And given that you will have the data initiated by the value, of course, and you have the P left equal to P left, and P right equal to P right. That's it. I also prefer providing another option for your constructor by moving the data into the node. So if that is the case, I'm going to have this just for fun. Okay, so that's it for the node. And all you have to manage here is the root of the tree. So we have a node, and we call that one root. Okay. Now it's time for us to make some public interface for our tree. Then we should have some sort of basic thing. The basic thing here is well, something similar to this. So you may have is empty, sign, something else. So let's say boolean is empty. Well, this one will return well nothing. Key root. So if your tree is empty, the root is null, right? What else? The sign. Alright, so sign T, Suppose that you have a method called sign. What should you return? Now, if you want to count how many nodes you have in the tree, it's very annoying because you have to look for the number of nodes on the left side, the number of nodes on the right side, and so on. So this is so bad. So I suggest that instead of doing that brute force searching, we just keep track of the number of nodes. That would be easier, right? So I'm going to add something here like sign t and elements. And from the beginning, I don't know, but I will initiate it later and return number of things. Let me have some constructor for the tree. So binary tree, the default constructor will be p root equal to node pointer first, and number of element is 0 by default. I would have some virtual destructor. Okay, and this one will do the clear job. I suppose. Oh, where is clear? I need to add the clear, right? So clear will be some sort of method. Return nothing, and it does something. Well, what do you think? Should I use recursion here, or should I not using recursions? Recursions? Easy for you to follow? Stack? Okay. Looks like you guys are scaring of stack and you prefer using recursion solution. That's fine. I'm not going to argue with you on that. That's okay to me. So let me make it clear, and what I want to do here is to release the data for the node. So I don't really need to modify that pointer, but I just receive the pointer out of the root. So I want to clear a subtree on my PR. What I do is I'm going to clear PR left, and what I will do next is clearing the PR right. Extremely easy. Finally, I would like to delete PR. That's all I have to do. But this only happens when PR is valid, which means if not PR, then I just return. Just for making it short, I write everything in the same line. That is not obviously not a good way to write code, right? Just for fun. So we have clear, clear, easy for this code, and that's it. So you have everything you need, the basic one. Then you may want to say, how about finding the height of the tree? Then let me say you want to get the height of the tree, right? So may I have the method for get height? And this one will, of course, return for you what? Yeah, height. But you start from the root of the tree. Okay? Oh, sorry, my bad. And if that is the case, we are counting something similar to the method over there. So you have sign t, you have get height. Easy, right? Sorry. And what you receive is the subtree PR. Now you consider in this one as the normal subtree. And in order to get the height of the subtree, if not PR, which means the tree is empty, the height is obviously 0. Okay? Otherwise, you need to calculate the height of the left and calculate the height of the right. So you may return the max of, sorry, do we have max? I guess we have some sort of yeah.
We should do something.
Yeah, we should include something, but no, that's too complicated. I just use that left case and right case. That's enough for me because anyway you have to initiate the left and the right in some way. So you could get page of PR left. Okay, and 8 equal to PR right. Oh, sorry. This one is going to get 8. Alright, so what you return is if left page is greater than right page, then you take left page, otherwise right page. That's it. Last one? Oh yes, that one. So I would return 1 plus this one. Wow, why this one looks interesting. This is the bad thing ever because we don't keep track of the height of every subtree. So whenever you query the height of the tree, you have to do brute force searching. So that is bad. But yeah, that's why I don't use that very often. I don't even care about the height of the tree. May you care, but not me. So we have insert, find, and remove. First, let's do insert. Void insert. Then let me have reference value. I want to insert this 1, 2, 3. So let me ask you, do you want this one to be done in recursive fashions, or do you want to do it by using iterative always?
Oh, yes, that's because let's do it because
Okay. All right. We will do both. I will have one version for this one, and let me have another version using iterative. So first, for recursion, I would insert that value into the root. So I will start with this one. Okay, that's easy. So in order to support that functions, I will have the main operations here. Insert to the root. Well, the root is a pointer to the node, but you may override that pointer. You may want to modify that root. So we have the reference here for the sake of modifying. You can use pointer or pointer if you want, but right now I just try to make it easy for you guys. Then you have the count t reference value. Okay, what we do is very straightforward. If the root is not empty, then you have to decide whether to go left or whether to go right. So if PR data, if data is greater than the value, right? Then you insert where? Insert that PR to left, that value, insert to the left. Otherwise, you would insert PR to the right, insert that value. Easy? That's what I want to do. Otherwise, you do what? PR equal to make a new node with the value. That's all. But remember, if this is the the case where you create a new node, this is better for you to increase number of nodes here for tracking purpose. Okay? Simple. This is it. This cannot be any easier, right? So don't tell me that working with a tree is hard or hard. No, it's not. It's simple. Free your mind. Now, some of you say, okay, what about iterative method? We will do something similar to what we have done with the list. So I will show you the way. Let me have the pointer up pointer. Let me start with the root. Then, what happens? Why? Why what? Why the root is not known? Obviously, if the root is not known, I'm going to locate the position where I want to insert. So, if what? If the node, if the node data is greater than what? Than the value, then you go left. If you go left, key equal to the address of what? The address of key left. That's how you go left, right? And if not, you go right. So we change this one. And as you exit the while loop, key point to the pointer, which is null. That is where you make the progress. P equal to new node with value and number of elements increase. That's how we do iterative method. Easy? Should be easy. Get used to it, okay? The reason why I say it's easy because if you take a look at the structure of that insert method, what you do is somehow tail recursion, similar to tail recursion, right? Because you call insert at the end. So that's tail recursion. And if you have tail recursion, in theory we can use iterative method instead. So this is why we have this one. Now it's time to play with find method. Well, find method return for you the pointer to the data. So maybe we have this find method. You may start with the key. Then this is the key you want to look for. Then what happens? For finding the value, you can start going by using that iterative. You don't need recursion, right? So let me have a node P starting with root. Okay. So why what? Why P? If P data is greater than the key, then you go left. P equal to P left. Out if what? If P data is smaller than the key, then you go right. So P equal to us equal to P right. Okay? Of course, if they are equal, you just return what? Address to P data. Okay, because you want to access that data. Okay, so if you exit the loop, which means not found, then you return what? null pointer. Oops. Easy, right? That's how we find one element. And remember, this one return for you the address of the first found. Okay, the first element you found. Now, if you look for all the elements with the same key, then you need to return it into a list, right? So, what should we do? May use provide that kind of feature. In that case, this is void, obviously, and this is find all. And if you find all key, then you need a list, right? List of what? T pointer, because this is what you have. And you need a pointer to that list. I don't know what list you provide for me, so just give me a list of pointer. And what I will return for you is, if it's smaller than the key, you will have that one, otherwise you will have this one. But this is where we struggling a little bit with the binary tree, because you need the very first occurrence. So you have PL insert what? Insert that data into the index. Which index you want? PL sign. I hate this. PL sign. Oh, you don't have? Get length, okay. Use different name anyway. Okay, we have that insert to the end of the list. And suppose that you have this set and what else? You will end up with the infinite loop, right? Right? You will end up with the infinite loop anyway. So we have to take this one off by break out of the loop. And as you exit the loop, what happens? We go all the way to the right. Because on the right, this will be equal, impossible. So, y p, we do this. If what? Okay, let me have p equal to p right. Okay, so yp is not known. Then if p data is equal to the key, I would insert to the end. Okay, so let me copy this one and put it down here. And as you insert to the end, you will move next by having p equal to p left. Okay? And otherwise, if the data of the node is no longer equal, then we break out the loop or we just return. We're done. We're done. Okay, so the purpose of the first one is to locate the key if it's found. And the first found here will take you out of the loop and we break. At that moment, we start going for the right side. So why this right side is not empty, then we check if the key is equal, we insert and we move. Oh, sorry, my bad. Not left. It's my bad. Sorry. It's so bad. Right, just go right, just go right. Because they are greater or equal. So just go right. Easy, right? Normally I'm not using the find all method. method. I will use find method only. But in case you want it, then you can have this implementations. Okay, last but not least, we have remove. So let me have void remove. What we want to remove is some key, right? Then what I do is I'm going to do it in the recursive fashion. So let me remove what? Remove from root that key. Okay? That's it. So looks like I need to implement some sort of method over here. Void remove, which the first one is the pointer reference, because I will modify it, and I will remove the key comes to reference key. Now, follow what we have discussed so far. The first job is always locating the positions of the key in the tree. Therefore, if what? If PR is known, then there's nothing for you to do. You just return, right? Otherwise, we have to concern about the value. So if PR data is equal to the key, well, this is where you remove. Let it be. Else, if the PR data is smaller than the key, greater than the key, sorry. If it is greater than the key, what happens? We remove on the left. Remove on the left. So PR left. Okay? Otherwise, we remove from the right. So we have here to right that key. So the first thing here, we set up the remove in the recursive fashion. That's fine. I don't mind it. But what about this? As you locate the position of the node we want to remove, then we have to decide which case we are in. 1, 2, 3, or 4. Then, if what? If PR left and PR right, both of them are not known, then we enter the fourth case, which I'm not going to do anything with right now. Else, if PR left, sorry. Left. This means the right is known, right? If left is not known, then right must be known. And if the right is known, what happens? The right is known. Let's go to this one, the case number 2. Okay? And if this is the case, I need a node from the P to hold PR, of course. What else? PR now will hold PR P left. That is right. So I have this one. And I would delete what? Delete P. Of course, in this case, the number of elements decrease. Right? This is like a single case. Otherwise, if PR P right. Now this is the case where we have the case number 3. So let me call the node. Okay. Let me update the root to be what? P right. And as you hold it, you delete P and number of elements decrease. Okay? The last case, which means both left and right are known, then your job is simple. Delete PR and set PR to none and number of elements decrease. Okay? So 3 basic cases is there. Your job now is hold this case, and as we discussed so far, we pick the minimum on the reference. So what do we do? Let me have a node P starting from PR P right. Okay? And what do? We go all the way to the left side. Right? So 1 P left is not known. I will have P equal to P left. Just like that. Oh, sorry. And as you finish this loop, we end up with the positions of the minimum of the right. Okay? And as you are at the minimum of the right, what you do? You ground the data. So P of data equal to standard. Let me move the data from P data to that node first. Okay? And as I move the data to that node, what do I do next? I try to remove it. Okay? So let me remove from PR P right. Remove what? Remove exactly the data we are holding at the current node. Okay? That may pose some sort of risk because it looks like I'm moving the data, but not copy. Yes, it's tough. So just to be safe, I will not move, but copy the whole data. By this approach, because I'm not sure during the process of moving data, do I move the dynamic data only, or do I move the data of the other objects? So it's a little bit of risky for me. Of course, I can move. So this is your choice. You have to put up some precondition for the user to use this one. If you say nothing, then we are not sure about the key. Okay, so the safe option for me is to copy the data. I will remove that later, but I want to make everything safe by just copy the data. Okay, so this goes like this. Let me copy the minimum on the right to the current node, and then I would remove the current node from the right side. Okay? And that's it. That's how you remove something out of the and remember, we will end up with the special case 1, 2, 3 over here. So we will always decrease the number of elements, and you don't have to worry. You do it once. And this is the part of recursion. This is where we handle the common case. That's it. That's how we do remove. Okay? Looks like we have something else to do. Traversal. Let me have void traverse. This one is like very annoying because you have 6 versions in total. North, left, right. If you traverse on the north, left, right order, then you have to traverse with another support function over there. Alright, so what you need to provide is a function. A function that return nothing and taking a reference to your data and do some job. You notice this is operations. And your job is to go traverse north, left, right with the boot from the beginning, and then you support the operation here. Okay, so this one is the support function, and actually that was function, and the one over there is just a wrapper. So let me copy the things. Then the first parameters will be the node of the subtree. What we do here? What we do here? You work on the node first, so let me call up, PR there, and then you traverse on the left side, so PR left with the off, and then you traverse with the right with off. Oh, of course, you have to check if PR is known, then you just return right. Alright, so let me make it short in one line so people can read it. Now we have that version, one version. Therefore, I should have 6 other versions. Okay. And let me do it one by one, otherwise right left. This is handful for me, I hate it. Right left, right first. So this one will be at the end, I suppose. No, I just changed the name. So right left. This one turn out to be okay. This one is in order. So you have left node right, and if you have left node right, then node will be in the middle. So put it here, please. But again, this one is left node right. Okay, this one also left node right. This one is going to be right node left, right node left. And if so, then up will stay somewhere here. Right node left, right first, and here, and right node left, and this is of course P left. Okay, sounds good. It's very painful. Left, right node. So as you have left, right node, then the node will always be the end. So cut it out, put it here. And this is left, right node, right. So left, right node. This one will be left, right. The last one will be right, left node. And of course the node will be the end. So put it down here. Right, left node. This is right. This is right, left node. And this is left. Okay, you can verify that one for yourself. Okay, I will not do that here, just to make sure everything is correct. And finally, I will update my functions again. 1, 2, 3, 4, 5. So may I have this node right left? Again, this one is node right left. This one is left node right. Left. Okay. Right node left. Okay, this one is left right node. This one is right left node. This is left node right, right? Left node right. This one is right node left. This one is left right node. Finally, you have this one. Right left node. Okay. So that's for that first traversal. Then finally, you should have another method. Should have another method for sorry, traverse breakfast. And you have standard functions over here. And that function receives nothing but t reference. Return anything, this is off. Well, I'm not going to write any support function because this one is supposed to be just like that. The only thing I did is the queue, but do we have a queue?
Yeah.
We didn't. Oh, too bad, we didn't have it. So let's make it.
Is there way not making a queue?
Sorry?
Is there way not making a queue?
No.
Function pointer?
No. We are going to use queue in this options. So I'm going to write something here. Let me borrow this one. The interface of the stack. But I will make it to be a queue instead. Looks like we are short on time, but that's fine. Like we try to do everything very complex at the beginning, but that's cause some trouble for us. And here's number Q. Okay. For Q we don't have push. What we have is a Q. We don't have top, but we have EQ. We don't have top, but we have first. We don't get top, but get first. Okay? So it looks like we done with the Q. Then let's make one implementation template. Class. Let me make a class for L1Q. This one is supposed to inherit from the linked list, right? Protect. Protected inheritance from the linked list, like L1 list of what? Of T. And this inherit publicly from Q, T. Okay, so let me clone all the thing here down. Oh, by the way, this should be public, right? I want Q. This constructor will construct normally, so I don't care. Okay, let the linked list do the job. This is the constructor where you will construct it from another queue. So I would like to construct L1 list T by using that queue. The queue is just a list, so it makes sense if I clone the list. This is the structure, so I will not do anything here. Okay, just let the list handle that job. You have the get length. For get length, what you return is L1 list T get length. Okay. Is empty. It just return what L1 list T is empty. For this, when you clear the queue, you clear the list. So, sorry, for L1 list T clear. Easy. I don't do anything special. Just dropping the method. So for this one, we copy things. May you return this? Fine. But before that, you may want to copy the queue here. So how do we do that? Well, it's a little bit complicated process. So I will let you decide what to do. But in this case, what I think you can do is you clone the list instead. Okay? So how do we clone the list? You consider that queue to be a list, right? Then you clone all the content of that list into your current list. So it looks like you have your, well, you don't need to cast things. Maybe not. Let's say, let me call L1 list T. Let me call operator equal, and let me pass the current queue to it. Can I do it? Yes. The operator is nothing but a function. So instead of writing it in a normal way, I implicitly call that function to block the data. Okay, I block the list of this one. What about the other one here? I guess the same thing applies. So I would copy this thing. Alright, and here is key, right? And if you don't mind, I would apply this rule just for sake, because normally key is already the double reference. I just want to make it safe. Now, what about the queue here? When you want to accuse some value, what happens is you have L1 list T insert that value into the index. The index is supposed to be L1 list T get length. Okay? That's it. That's how you accue. Accue at the end, right? And you have the value here. Same thing applies, so I'm going to copy the whole thing, put it down. If you want to be safe, you may want to enforce this one using the move, but I guess that's the same. How about the queue? Well, the queue requires you to do list T, remove where? Remove as 0. You don't care, right? Is that the beginning? The first, what you return? You return the list T. How about begin? Can I do so? Why not? Makes sense, right? What about get first? Oh, same thing. So I will copy it. Okay, so that's conclude my implementation of the queue. So what we do now is we perform traversal of the breakfast order. What do we do? Let me have a queue. Oh, sorry. Now we have our one queue of note. Okay, let me have a queue. And of course, if the root is empty, then nothing for you to do. I will finish that there. Otherwise, I will have a queue that what? Root. So the process is going to be y. The queue is not empty. I'm going to do something. So let me make a note. P, getting from the first of the queue. Get first, fine. Then what do I do now? What do I do now? What do I do now? If what? If you have some left tree, then you unqueue that one. So if P left is valid, then Q will unqueue P left. Likewise, if P right is there, you have P unqueue P right. And finally, what do we do now? We can either process that P data here, or you may process it earlier. This doesn't matter because the left tree and the right tree will wait to the end. So finally, we queue. That's how we traverse the breakfast order. Extremely easy, right? So that's everything you need to know about the binary tree. Easy, right? So let's try to work out at home, and hopefully if you can verify this implementation by yourself, then you understand it and we can move on to maybe our next class. Okay? See you there.